Cool. Started recording.
Good.
Hello, everyone, and welcome to another Flan Talk. Today we have Anej Svete here, and he's going to talk about transformers can represent Ingram large language models. Thank you for being
here. Thanks, Lena, for the introduction and also for the invitation. Yeah, and thanks, everyone for having me and joining. I haven't actually been at many Flan Talks, as ashamed I am to say it. So I'm not entirely sure how what the format is, but I'm gonna try to basically give you a picture about what this is about. And it's gonna be no slides today. It's gonna be me writing on the iPad and kind of explaining things as I go. And how I imagined this, let's say, is first I'm gonna talk about let's say why we even ask this, and why this particular kind of paper and this particular question, and then after some, let's say, background. That I don't think that there's going to be much to introduce. I'm just kind of I'm just gonna, let's say, agree on some notation. I'm just gonna talk about the let's say construction, so some technical parts, and then we're gonna end with some, let's say, discussion. And I think a nice part of doing something more kind of handwritten is, I think there is more time. It's going to take a bit longer for me to write stuff. And if you have any questions and you think of anything while I'm writing, please, you can interrupt me whenever you want. I think it's going to be better that way. Anyway, so basically, I mean, this is one of the papers where the title says almost like reveals most of the content. We kind of looked at transformers as language models, as these autoregressive, causally masked language models, and wanted to see not just what types of formal languages they can represent or they can simulate, but we also wanted to kind of see or figure out how to look at transformers as really distributions, or how they implement distributions. And for some reason, or like for a few reasons I'm going to talk about later, kind of n-gram language models were kind of the logical first step in this kind of in this journey of trying to understand what transformers can do in terms of probability distributions. So this is, kind of throughout my PhD, ever since I started with Ryan, a few people in the lab have been, asking kind of these similar questions, either about RNNs or transformers, not really what kinds of formal languages, not just what kinds of formal languages, what kinds of automata these neural models can implement, but also what kinds of probability distributions they can do. And maybe why this is relevant, let's say, is well, because how we kind of think of a language models formally is that a language model is a distribution over it's a distribution over some set over sigma star, where sigma is, of course, an alphabet. I'm not gonna give all these trivial definitions today. This is just something, as this is something kind of core to the paper, so I'm just gonna have it written here. Hopefully is well, like, I'm gonna keep maybe returning to this, and if we look at really language models, or if we kind of internalize this definition and internalize the language model is a distribution over sigma star, a natural question is then not just what kinds of automata it can simulate, but also so I'm gonna write a natural question: what let's say classes of LMs, so distributions over strings, and let's say a neural network, e.g. a transformer, represent. So this is kind of, let's say, this has been a core question for a few of my papers, recently, and yeah, this is the question we apply to transformers in this particular paper, where we kind of see, more concretely, not this, more concretely, kind of what's the, let's say, relationship between transformers and n-gram language models. Okay, so this is really the very precise, or not, let's say, somewhat precise question that we try to address here. And as with most of the kind of work in this area or of this nature, we try to see, can a transformer, whatever we mean by a formalization of a transformer, can a transformer implement or represent any n-gram language model? And is there anything else that transformers can represent? Of course, we don't talk about the latter so much in this paper, but of course, yeah, transformers can do more. But really, the core question, and also, let's say, the result is that of this paper is that under the right assumptions, transformers can, of course, represent n-gram language models. And we kind of gave a few constructions or a few ways, a few mechanisms in which they can do this, which I think, at least for me, it was kind of a learning experience as to how transformers can do certain things. Maybe I found since then a few kind of similar constructions in other papers. So I guess people have been aware of this, but for me, it was kind of something that we had to figure out on our own. So kind of with this, let's say, question, maybe I'm going to give, the answer that we kind of formulate more formally in the paper, but kind of the answer kind of goes something like, let's say, transformers can represent, let's say, n-gram LMs. I'm going to make this a bit more precise later. Okay, but so that's kind of, let's say, an outline of what the paper does. This was just very, very, very quick, and just to kind of give you a picture of what this is going to be about. But yeah, let's make these things a bit more formal now. Is anything? Yeah, everything clear so far? If you have any questions, feel free to interrupt. Okay. Now, I assume, hopefully correctly, that I don't have to talk about what how transformers work. I'm gonna I'm gonna give or explain in more detail what kind of assumptions we make, or what if there are any kind of particular decisions that we do that we make that aren't standard. I'm gonna touch upon those later. But again, just to have it written down and kind of to be able to reference it later, I'm going to define n-gram language models, even though, yeah, they are very simple. So let's say, so yeah, we said that a language model is just a probability distribution over strings. So maybe I can write it like so. And yeah, we have this sum is 1. I'm going to write this y vectorial instead of bold y for strings in sigma star. And yeah, so most language models, or yeah, basically all of them are defined autoregressively, where we decompose the probability of some string, which I'm going to write as a concatenation of some t symbols. This is the probability of EOS given the string and this product of conditionals. This is y less than t from 1 to t. And the crucial assumption that the n-gram language models make is this n-gram assumption, which is the kind of the assumption states that the probability of the token t given all the previous tokens, which are in principle required here, this only depends on the previous n-1 tokens. So we would have p of yt given, let's say I think it's, I always mess this up, I think it's t minus n plus 1 up to t by t minus 1. So basically the previous t minus 1 tokens. If I kind of write this, let's say a bit more concretely, if we have t minus 4, if we wanted to compute the probability of this token yt in, let's say, a 4-gram language model, we would only have to look at the previous three positions to kind of determine the next the probability of the next token. Okay, and it's a bit kind of, it's almost, I mean, it's kind of, it makes a lot of sense that transformers that can by construction can look at the entire string that kind of the entire prefix while computing the probability of the next token. It's kind of like intuitive that yeah, they would be able to somehow get all, they have all the information that n-gram language models have plus more. Of course they can they can look at these three positions, but also they can look at much more in the back. But if we're being precise, it's not just about having access to this information. The question then really becomes, can we construct a transformer kind of formally by setting weights and all of this MLPs and stuff? Can we set them such that really the transformer only attends to these three positions and kind of only takes into account the information here and kind of is not distracted by everything else that happens kind of further back in the string, so that it really computes the probabilities that we care about, exactly the ones those from the n-gram language model. And yeah, this is so this was these were n-gram language models. I hope this was this somehow somewhat makes sense. And this is kind of the only, let's say, thing that I want to say about our version of a transformer, which is let's say I'm just gonna write our model of a transformer, which is it's fairly standard, especially for theoretical work. Let's say I'm gonna just write a few, let's say, assumptions or modeling decisions that we kind of decide on. The first one is, well, as I said, we use masked, causally masked, I think it's some people call them. Transformers. And well, we ignore layer norm. It was just inconvenient to deal with, and we're kind of interested in lower bounds anyways. And while layer norm is kind of has been linked to increasing transformers, kind of representative expressivities. So we ignore it here. We do have residual connections. We do have all of that. The big kind of question that makes a bit of a difference here is the type of attention. So I'm going to write it in orange here because it's important. Type of attention. And there are kind of three actually types that we consider. And well, let's say one of them is not in the paper, but I talked to David Chang a bit later about it, and he told me how to include it as well. So I'm gonna briefly touch upon that as well. But yeah, so first we use kind of standards for let's say theory. Most of you are must be very familiar with it, which is hard attention. In this case, it doesn't really matter whether it's uniform, so whether it's averaging or unique hard, we kind of both work because in our constructions. Then we have the second choice is something that we call sparse attention, which is attention, but with a sparse max normalization function. I'm going to introduce it in a second. And then we have soft attention, which is not in the paper, but let's say it's in my head. I still have to write it out. But yeah, I may just mention it here for completeness. Okay, so we like the only real kind of thing that we play around about transformers here is what kind of attention they use, and then we have a few different, let's say, results based on that. Okay, so with this, let's say, background out of the way, let's, I guess, recap. We want to know what kind of, what's the relationship between n-gram language models, sorry, transformers and n-gram language models. In particular, we want to show, as I spoiled, that that transformers or causally masked transformers can represent n-gram language models. Okay, let's start with maybe let's start with hard attention transformers, or yeah, the argmax case. So okay, I'm gonna write. So I wrote, yeah. So I said transformers can represent n-gram language models, and I'm gonna now ask the question: how can hard attention transformers, let's say, express n-gram LMs? And to kind of have this lower bound on, yeah, transformers can represent n-gram language models. It would be enough to sketch one construction and be like, yeah, this works. But really, for me, when we were writing this up and figuring these things out, it was more about learning how transformers actually work and how they can work. So we came up with a few alternative, let's say, ways that they can do the same thing, which I feel like for me it was a bit it was instructive in what they can do and kind of how they work. So I'm gonna briefly mention two ways that they can do this. They can represent n-gram language models. So first one is with n-1 heads. And this was kind of the first thing that we came up with. Actually, it wasn't us. I have to say, at some point when we were first thinking about this, which was a while ago, Ryan was talking to some people on Discord, on Flan Discord. A few people engaged in the discussion. I don't know exactly who, but I know that Will Merrill kind of just dropped this idea about the n-1 heads. And yeah, it was something that worked. So I have to thank Will for the idea here. And kind of the intuition behind this first construction is each of the heads has its own independent parameters. Kind of among others, it has its own way, or its own query and key entries or vectors, which means that it can kind of we can construct each head to look at a different position. And because it's we talk about hard attention here, we can kind of instruct each head to look at one particular position in the string so far. And if we have n-1 of them, we can simply have one head per symbol that we care about in the previous n-1 ones. And that gives us the whole context that we care about and nothing more, which is exactly what we need. So I guess more pictorially, this is the only, let's say, useful picture that I found from the paper to kind of show something here. I'm gonna paste it in the slides or in the notebook, so I can maybe talk about it a bit more. Which is, yeah, maybe I should have addressed this earlier, but basically this is the whole intuition behind it. We have some string where we are predicting the token YT, or we are modeling the probability of YT given all the previous tokens. Now, if we want to simulate a 4-gram language model, we have to figure out, or we have to, I guess, identify the previous n-1. So 4-1, three symbols. And for that, we have 3 heads. And each of those will kind of, with its hard attention head, will put all of its attention onto exactly one position, which is going to be, well, for each of the heads, its own position. The first head is always going to look at the symbol that came one step back. The second head is going to look at the position 2 steps back, and the third head is going to look at the position 3 steps back. And because we then have this head combining function h here, this can kind of just concatenate these three encodings, and we can basically, in a sense, just look up what these probabilities are, because in an n-gram language model, by definition, we have a finite number of different next symbol probability distributions. So this is the idea here. We have one head per position that we care about, and the, let's say, construction here is fairly standard. I'm not gonna go into the details too much, apart from like one thing that confused me until really I thought about it a lot, which is, I guess one of the first papers about the expressiveness of transformers. One of the first papers was Michael Hunn's limitations of self-attention paper from 2020, where he shows that soft and hard attention transformers struggle with parity, for example, and I think Dyke languages. And like one thing that like just didn't kind of come one aspect in which things just didn't match up for me was, people talk about usually like the assumptions of, maybe do you have layer norm, and what kind of attention do you have? But then I think there is one more, one assumption more that people don't really mention. I don't think is as important, but still something that I had to wrap my head around, which is, let's say, one neglected aspect are the positional encodings bounded. And I don't know, like I maybe this is something that everyone is familiar with, but I just needed a long time to figure it out. But like Michael's soft attention results, where he shows that that the cross entropy converges to 1 for parity, this all assumes bounded positional encodings, which, in standard transformers, that's the case. If you have the sinusoidal encodings, that's completely fine. But really, like, basically, the proof relies on some Lipschitz properties of the maps, and there you really need the fact that the inputs are bounded, because basically, if they are not, you can basically construct you can use the positional, let's say, the larger and larger gaps between positional encodings to kind of put the attention mass whatever you want. So yeah, this is just, we kind of, I thought that, I saw that I had a construction with soft attention that was able to do not parity, but this n-gram language models, and it was confusing me a bit. And then yeah, basically let's see, the epiphany that I was missing is, yeah, I was using unbounded positional encodings, and then if you want this Lipschitzness and stuff, people assume bounded positional encodings. And yeah, basically, why I'm mentioning this is because this is one of the let's say the only difference that I'm gonna mention between let's say the representational capacity of hard attention transformers and then soft and sparse attention transformers that I'm gonna talk about in a few minutes. So and kind of the difference is in hard attention transformers, because we have this very discontinuous way of assigning attention to different positions, we can't even have bounded positional encodings. They can be bounded between 0 and 1. We can have like units. We can have unit length vectors and stuff like that. So these positional encodings can all be bounded, and basically the hard attention just kind of makes us not care about Lipschitzness. And again, I don't want to get into the technical. Again, I'm not sure how technical these talks usually are, but I don't want to get too technical about how these heads are constructed. The idea is just that it's all about the positional encodings. Basically, when you when this head is figuring out where to put the attention, it's just going to look at, okay, what is the positional encoding of the thing that I care about? And then it's going to we construct the positional encodings that are kind of transferred into the key vectors, such that, yeah, exactly like exactly this kind of these positions are attended to. It's not, we don't care about the values or whatever. It's just about the positional encodings that we put in at the beginning. And this can be, as I said, this can be unbounded or bounded. For example, the simple way to do it is to use something like, well, just P. So positional encoding at time T would be, say, PE of T would just be T. Another one where if you wanted to have something unbounded, we could have something bounded. We could have PE of T be this unit vector, which is, I think, let's say 1 over T plus 1 and 1 minus 1 T plus 1 or something like that. This gives you a unit vector, but it doesn't matter. The key thing is, in hard attention, we can use both of these and it's fine. Okay. This is, so to kind of zoom out a bit, this was the question, answering the question how hard attention transformers can express n-gram language models with n-1 heads, where, yeah, each of the n-1 heads just has its own parameters and it does its own thing. Are there any questions so far? Okay, good. If not, I want to briefly talk about the second, or the kind of case B, how like, let's say, the other way that transformers can implement this, which is with n-1 again layers. where the idea is sort of similar, but sort of also not. And it's a bit less intuitive, but I think still quite okay. And in this case, let's say the key aspect is or are residual connections. And the point is, again, just to sketch this out. Suppose that we have some string y1, say yt minus 4. Again, if we had, let's say, a 4-gram language model, so we would be interested in the previous 3 symbols in the string. So these 3, when computing the probability of this one. In the previous construction, or the previous way to do it, we would construct 3 heads here. Now we're gonna construct, or let's say, somehow put here 3 layers. And what this is gonna do is basically in the first layer is just gonna copy over. So the first layer, let's say at this position, at position t minus 1, this one is just going to copy over the representation of yt minus 1. And, because, attention does this at all positions at once, but I don't really care about these ones at the moment. Sorry, I just made a mistake. No, it's not gonna copy over the same thing. It's gonna copy over the thing from the left. So it's gonna kind of, through the residual connection, it's gonna keep whatever already is here. So the representation of yt minus 1, and it's gonna add, by attending to the previous position, it's gonna add yt minus 2. Exactly. And then so this is going to be it's the first layer, and then at the next step, this is going to be added. So again, the information that we already have here is going to be kind of copied over with the residual connection, and then by attending to the position one step back. One step further back, we're gonna kind of copy over the position or the symbol that's even further back into kind of the position here. And again, with n-1 steps, I guess even n-2 here, you get all the position, all the symbols that you need in one place, and then this allows you to, let's say, just in a similar way to here, just kind of combine these layers and index the conditional probability that you care about, and kind of then you're happy. Then you're simulating your n-gram language model. Okay, so this is a bit less intuitive, but I think it's like just a nice way to see how, for me, again, when I was writing this, it was a nice thing to see how transformers can do the same thing, relatively simple thing, in 2 orthogonal ways. Okay, and then so this was about hard attention. Now I want to let me briefly talk about actually soft attention. So case number 3 from above, soft attention first. I don't want to say too much about it because most of the results that I just mentioned can actually be just transferred from the hard attention case, but importantly with unbounded transitional encodings. Again, this is kind of something that I talked to David about, and there is a way to basically construct an MLP, after every layer here, of course, there is like an MLP doing something with the representations, and there is a way to use these MLPs to kind of cut off the parts of the string that you don't care about. So basically the potential weights that are not large enough, you can kind of cut them away. And this is the intuition of soft attention in this case. So you can say cut off the small attention weights. But for that to be possible, you need unbounded PEs. Exactly. So, but basically, you can do both of these things again. You can do n-1 heads where you really kind of focus on one head, and you talk about or you can talk about n-1 layers, but you just have to have these unbounded positional encodings. But yeah, I mean, this is of course, the most realistic of the settings. This is what people implement, and it's just nice to be able to say something about this. But this brings me to like the compromise of these two worlds, which is sparse attention, which is something that I haven't seen people talk about much, but I just like the idea, which is basically you can it's a way to be able to have 0 and 1 attention weights, let's say, without having and still have like a differentiable transformer. Of course, with hard attention, nothing is differentiable. You just have these step functions. But sparse attention is uses the sparse metric normalization function. I'm gonna mention it in a second. But yeah, the key idea here is, well, in comparison to even averaging hard attention, it can assign 0 and non-zero attention weight, where the non-zero ones can be different. In averaging hard attention, we have either 0 or 1 over the number of elements in the argmax set. And secondly, it's also differentiable, which is nice. Okay, so just to contrast it to what people usually do, which is soft attention, which uses softmax, where softmax is defined, as all of you know, softmax of some vector x at index d is exponential of xd over the sum this way. And this is, this is very standard. A lot of people use it. And it also has some like dual form where it's like the optimal, what is the optimum of some optimization problem. I forget which one it is. I mentioned it because then we have sparse max, which also has like a formulation like this, but it's a bit more complicated, and I don't know it by heart. But the optimization, let's say, form is much easier. And let's put it in orange because it's new. And it's defined as sparse max of some vector x is the arg min over z in the probability simplex, let's say d minus 1, of this optimization problem. So x minus z, kind of this second norm. So it's basically just the projection of this vector x onto the probability simplex. So this this projection in this sense. And because of this, it also it can have many zero entries, which is very, very attractive. Among other things, like one simple thing that we show in the paper is that you can simulate hard attention with it, which means that you can basically have you can single out one single position, which is the idea here is, whereas you might have kind of hard attention that if these are positions between 1, 2, and so on, hard attention might do something like this, where it kind of singles out one position, where this is 0 and this is 1. What soft attention could do is kind of really hand wavy, would do something like this. It's still a continuous function, but it can do something like this. So kind of really all the values are still 0, whereas the one you care about is 1. But it can also do other stuff. It can you can have something like this or whatever you want with sparse max. Okay, yeah, it just has to sum to 1. But yeah, I just kind of find it cool. The one thing that, of course, so because of this, let's say, equivalence kind of shown here with green, again, both of these results with n-1 heads and n-1 layers still kind of directly map to the sparse max case. However, again, we need unbounded positional conics to be able to do this. Yeah, you still need unbounded positional encodings. Because basically this is still kind of Lipschitz enough to not be able to counteract the fact that you have unbounded positional encodings as the string length increases. If the string length is arbitrary. Okay, and then the reason I really wanted to mention this is we didn't have any experimental results in the paper, in the theoretical paper first, but since then we kind of ran a few experiments on kind of how well transformers can really approximate also n-gram language models with kind of this setup with soft attention, with and also with sparse attention. And actually, it seems like because you can still train with sparse attention, you just kind of replace the mutation of attention weights with this, and there are efficient PyTorch implementations of this. Like sparse attention transformers actually do better on this very simple, n-gram language models. It's like I haven't analyzed kind of like the attention patterns yet, as to like where they exactly put attention, but I just find it very very fun and kind of satisfying that actually if you use something like this which kind of really can zero out positions it doesn't care about, you do or the transformers do better. I don't know, did I hear something? Did someone unmute themselves, or was that just some noise?
Someone rejoined and had themselves.
Okay. Well, actually, because I mean, this is kind of the I guess the one of the main takeaways from this paper and kind of the presentation that I wanted to get, which is sparse max attention is something that I find interesting, and it seems to be it seems to be as fast, and at least on these very simple languages, as stable as soft attention, but it's just something you can also train, and it seems to do better on these models. But yeah, again, I'm not sure how long these presentations usually ask. I wanted to keep it not too long to also allow for some discussion and kind of to hear some of your questions or thoughts. But yeah, I think this might be a good point to end it. And just kind of to recap, we wanted to take this perspective of analyzing transformers with formal languages, with kind of very with connecting them to very precise mathematical computational devices. But instead of looking at classification of strings, instead of looking at simulation of automata, we wanted to take this more probabilistic perspective and for that, like the obvious first step is one of the simplest things that people have used, which is n-gram language models. And maybe the one thing that is important here. So I talked about hard attention and sparse and soft attention and this construction with n-1 head and n-4 layers, which I hope it wasn't too convoluted. Like one kind of maybe other thing that I wanted to emphasize is why we talk is kind of besides simplicity, why we also thought about n-gram language models is because, like transformers and unlike automata and many of these other things, n-gram language models are also very parallelizable. You really just care about the previous n-1 tokens and you forget about the rest of the string. So you can do many of these next symbol computations, in parallel, just like transformers do. But then, we didn't know enough about circuits and logic to kind of take that perspective and try to make it probabilistic. And then, as I said, there are these multiple ways to simulate n-gram models. And people, I don't know, n-gram seems like, I don't know how much there is to this, but n-grams seem to kind of pop up in a few places for transformers. Also in context learning, people have these induction heads that are basically just n-gram heads that kind of look up individual patterns. And so it seems like n-grams might be there might be something about simple n-gram statistics that transformers really rely on. So to have just like a concrete technical way of looking at how they can implement them was just a bit, was I'd say pedagogical and instructive for me. But I'm gonna end it here, and I'm happy to discuss anything. Thanks.